Hey everybody, can you guys hear me?
Yes.
Okay. Uh, grab a sheet of paper, blank paper, use the calculator. I'm going to give you a question in just a couple of minutes. So the quiz you'll need for notes that you've been taking on a couple weeks. You'll need your calculator and you'll need a blank sheet of paper. So go ahead and grab that stuff. We'll get started in just a second. Okay, can you guys hear me? Are you able to see the quiz?
I hear you.
Okay, so on your paper, here's a circuit. 25 volts, resistor, 12.56 ohms, inductor, 100 microhenries, capacitor, 253.3 picofarads. This is a series resonance circuit, and what I want you to find are these values. Give me the resonant frequency. I want the bandwidth. I want the Q of the circuit. I want the maximum current in the circuit. That's the current at resonance. And I want the power at the half power point. You can't read that. That says PHP. That's the power at the half power point. So you can use your notes. You can use whatever. I'm going to give you about 15 minutes to do this. It shouldn't take you 15 minutes, but what's going to happen is I'll come back in about 15 minutes. I'm going to have you text this to me. You got to do it within that time frame. Anything past the time frame that I allow, I'm not going to count that. So when this is done, if you text me the answers, say 5 minutes after I say it's time to text the answers, then you missed the quiz. So go ahead and work it out. 12.56, 100 microhenries, 253.3 picofarads, 25 volts. I want the resonant frequency, bandwidth, Q, Imax in the circuit, P at the half power point. See what you can do with that. And then be prepared to text me the answers. Okay, guys, in about 1 minute, I'm going to ask you to text me your answers. And I have the way I want to text right here. Your name, EET 132, and then your answers for these, 1 through 5. So you got about 1 more minute of working to do. All right, so now you have about 1 minute to text me your answers. So go ahead and text. If you don't have the number, I will put it on the board, but you should have it. You're going to text it to 4946162. So text your quiz to that number. You need to do it within the next 60 seconds.
Just want a picture, I guess, or should we text you the answers?
You can text me the answers.
He told you to text me the answer.
What?
If you want to send a picture, you can do it as long as I can see it. I don't mind that. It's up to you. But I gotta have the information, your name, answers, all of that. I don't know what you guys are technically capable of. Couple more seconds and I need them. Okay, the quiz is now closed. If I get any text after this time, I'm not going to count it. So hopefully you got your answers to me, and hopefully you got the right answer. We will see. Okay, well, we're going to go ahead and get started. Before we do that, a couple things. So I did make a journey up to the school today, and it is, in fact, open. I went inside. I sat in my chair in my office. It was nice to be there. I did talk to the lead tech about us coming up there. Well, I already talked to him by phone anyway, but he emphasized the fact that he's in agreement. I saw the dean, but I wasn't able to talk to the dean because he was in a meeting. So I think it's going to be a go, but obviously it won't be this week. Room 207 is, well, you probably don't know the room. It's a room directly across from the lab center. So it'll be one of the rooms up there, and it'll have to be next week. But it looks like it'll be all right. Now, what I like to do is just continue meeting up there until we're done. But I don't know if that can happen or not. We'll see. So I know some people had some concern with some times. There were some people that were working, people doing childcare. Don't worry about any of that. We'll be very flexible with the schedule. We'll work around any issues that come up because I know we have planned to do this thing by remote. So I don't foresee any problems at all. The other thing is I kind of got ahead of myself yesterday. If you remember, we talked about series resonance, and I was supposed to briefly talk about parallel resonance and then go into transformers. I think I was wanting to get into transformers so bad that I didn't talk about parallel resonance. So I want to say a few words about parallel resonance, and then we're going to go back to our topic that we had started, which was transformers. So let me say just a few things about parallel resonance, and then we'll get into some more transformer exercises. And I do have homework for you. I know I've been giving you an assignment in a while. I have 2 transformer homeworks. One, just practice what we're going to do today, and then the other will be a topic that we may or may not start today called impedance matching. So I will post that right after class, but we might not be ready to do everything on there until the next lecture. Just depends on how much stuff we get through today. So let's talk briefly about parallel resonance. And all I'm going to do is I'm just going to talk about how it differs from series resonance. And I'm not going to give you any more kind of quiz or test other than what I just gave you. So the focus was on series resonance. Parallel resonance is this, though. You have a voltage source and you have parallel capacitor and inductor. So in communications, when you have that circuit where you have a resonance circuit like this, it's called a tank circuit. It's called a tank circuit, and that's used widely in electronic communications for tuning when you go from one station to another. So this LC circuit, tank circuit, is used extensively in electrical communications. Of course, this is my power source, and this is my capacitive element and my inductive element. And you might be thinking to yourself, well, hold on a second. What about the resistor? Isn't there a resistor in there? And the answer is yes, there is. Typically what happens, remember in DC when we talked about the resistance of wire, it's rho L over A. We talk about the resistance of wire. Typically what they'll do is instead of putting a physical resistor in there, sometimes they put a physical resistor in there. But you can use a resistor of the inductor. And the way they do it, let me show you how they would write that. So what you would do is just show a resistor and inductor. They usually call this R sub I. That's R sub I, and that stands for internal resistance. That is the internal resistance of the wire. So it's not a physical resistor that you solder to the wire. It's just the resistance of the wire itself. You can use that for the resistance of the circuit. And then this will be your C element, and that would be your L element. But to show that that's not a separate resistor, like a freestanding component, to show that, they usually put a box around the R sub I and the L. So you know it's all one thing. So they'll put a box around. Well, this marker's not working. Like this. Most of the books that I've studied will do this. And then you know that the inductor and the resistor are just all one thing, all one coil. And then you can treat that, if you knew the ohmic value of it, but you can just measure it with an ohm meter. You can treat it as if it were a freestanding resistor, if you needed to do that. But in the parallel resonant circuit, what happens is the line currents are out of phase by 180 degrees. So what do I mean by the line currents? Well, the current in the capacitor and current in the inductor are out of phase by 180 degrees at resonance. So at resonance, you have a current flow in the capacitor. We'll just call that IC. You have a current flow in the inductor. We'll call that IL. So ideally, if you think about it, if the capacitor current is flowing this way, and the inductor current is flowing around this way, then the main line current will be 0. So ideally, in the perfect world, with a resonance circuit, parallel resonance circuit, the currents will cancel out. Remember, in the series resonance circuit, it was the voltages that canceled out, the ohmic values canceled out, and you get maximum current. Well, here, it's the line currents that cancel out. Well, if you had the line currents cancel out, in the perfect world, they cancel out completely, and the net current, that's the line current, the net current in the circuit. Now, when I say net, there's current here. If you put an ammeter there, you would measure a current. If you put a current on this branch, you would measure a current. But if you put a current in this wire or this wire, anywhere else in the circuit besides in the tank, you would measure 0, ideally, 0. And then if you try to figure out the impedance, that would be the voltage over the current, which is equal to the voltage over, well, ideally, the net current will be 0. So you got a value over 0, which is infinity, which means that the impedance is really, really high at resonance. A high impedance is just another way of saying a low current. You might say, what do you mean infinity? You really can't get, well, we're talking ideal. Ideally, you wouldn't have any resistance right here at all. The coil, the inductor would be 0 resistance. And then this would be true where the current from the inductor and the current from the capacitor will be equal magnitude but opposite direction because they're 180 degrees out of phase, and they will cancel out. That never happens because you can never get rid of the resistance of the wire and the inductor. So these will never exactly be totally equal to each other, but they'll be just a little off. And what you get is a very, very small current right here, because that current is the difference between the inductor current and the capacitor current, and that's approximately 0. The closer these are to each other, the closer the answer is going to be to 0, and that's only offset by that internal resistance of the coil, the R sub I. But here's what you can take away from this, is that at resonance, in the parallel resonance circuit, the impedance is really, really high. If the impedance is high, if the opposition is high, that's another way of saying that the current is low. And so one way that this differs from a series resonant is in the curve. Let me draw the curve for you. Actually, 2 curves. The curve for current, remember in the series resonance circuit, kind of like a bell curve? Well, in the parallel resonance circuit, since the impedance is max, the current is min. So here's what you have. This is my center frequency, my resonant frequency. The curve will look like this. And this is frequency versus current. So it looks like an inverted bell curve. You still have values that you can calculate if you wanted to. I won't go into it here. I just want to show you the other curve. In the perfect world, this bottom part will come down here to 0. It doesn't because of the R sub I. You can never get rid of that. But if you could, this would go all the way down to 0. If I have a current curve that looks like that, if I made a curve of impedance, it would look like this. This is impedance in the circuit. Now, again, the impedance in the circuit is going to be maximum because my current is minimum, so it actually is going to look like this. The bell curve that we looked at in the series resonance circuit. So a parallel resonance circuit has minimum current, maximum impedance at resonance. A series resonance circuit is the other way. It has maximum current, minimum That's the main difference between the two. Now, we could actually get into some calculations with this, but I'm not. I just want to introduce the topic of resonance to you. We study series resonance, and you understand what it means. All the other formulas are the same. The formula for resonance, you would use it for a parallel resonance circuit or a series resonance circuit. It doesn't matter that they're in parallel or series. You still have the L, the C, and so forth. So that's all I want to say about parallel resonance. And I don't think I'll be having you do any other kind of quiz or anything other than what I did today. So you're not responsible for anything. I just want you to have the knowledge. And where this comes up is if later on, definitely not in Cincinnati State, but later on, let's say you wanted to go to UC and get your bachelor's in EET, you will take a class called Communication Electronics, and then this stuff will kind of come up. You go more into detail in the tank circuit, tuning, and there's a whole lot of stuff you could actually go into if you wanted to. But that's kind of beyond the scope of the course. So just kind of realize there's this thing called parallel resonance, and then that is kind of the opposite of series resonance. One has maximum current, one has minimum current, one has minimum impedance, one has maximum impedance. And that's really kind of all you got to know for what we're going to do in this class. Anybody have any questions over my brief presentation about parallel resonance circuits?
Yeah, what does it say after it says the current of L minus the current of the capacitor?
Right here.
What does it say to the right? Yeah, what are those two?
Oh, let me make that neater. It says the current in the two branches. What I want to write is this, right? That they cancel in the main line, but what I wrote over there, what you couldn't see, was this. They're approximately equal to 0. So because of that resistance, if you can get rid of that R sub I, then I can make that an equal sign. But there's always going to be wire resistance, so you can't really, there's no way to get rid of that. So it's going to be very close to 0. So that's what that means. So, you know, just depending on what you can do, you can almost assume it's 0, the current. If you're doing some kind of practical application, you probably can assume that the mainline current is 0 for whatever application you're doing. So that's all that is. Anybody else? Okay, well, I'm done with the resonance stuff. Let's turn our attentions back to transformers. And if we do, or I shouldn't say if, when we do go up to the lab, I think one of the labs I want to do is a transformer lab because they're so easy to understand and they're just like right there. So we'll do something with transformers and the O-scope and all of that. But let me just remind you kind of where we left off real quick. Who can tell me what transformers are used for? We talked about 3 applications. What are they used for?
Step up the voltage for
Yep.
transmission, and then step it back down on the other end.
Okay, so we can use it to step up the voltage. We can use it to step down the voltage.
And isolation if the coils are the same on both sides.
So isolation. So this happens, we talked about this thing called the turns ratio. The turns ratio was defined as the ratio of the secondary number of turns to the ratio of the number of turns on the primary coil. We define that as little n, the turns ratio. And we said that turns ratio is greater than 1, then we got a step-up transformer. If it's less than 1, we have a step-down transformer. And if it's equal to 1, then we have an isolation transformer. And in reality, no matter what the turns ratio is, all transformers are isolation transformers because just by the nature of the way they're built, the primary coil and the secondary coil are 2 separate circuits. circuits. They're not physically connected. They're linked through the magnetic field. But if you use it for the purpose of isolation, just strictly isolation, then you have a turns ratio equal to 1. And so we won't get into this. We've talked about step up and step down. We'll do some calculation. You do some with your homework, some calculations. But there's one more application of transformers that we'll talk about. I don't know. We might do it, or probably do it next time. But the other application, there's 4. You want to remember all 4. The very last one that we'll talk about is called impedance matching. So after class, what I'm going to do is I'm going to go up and I'm going to you got 2 homework assignments. I'm going to put them up on Blackboard. The second homework, part 2 of the second homework, deals with this. And I don't know if we'll get to this today, probably not. So if you start the homework, just first homework assignment, which you'll be able to do after today's lecture. And if you want to start the first part of the second part homework, you can do that. But you won't be able to do impedance matching until we talk about it, because I got to derive some formulas. We got to talk about a little theory. So that's the second page of the second assignment that I'll post to Blackboard. You'll see what I'm talking about when I do it. So we talked about that. We talked about the symbol for transformer. Let me put that on the board. The symbol's like this. There's 2 coils close to each other. Usually, if you have some kind of core material, if you show nothing in between, that means you have an air core. If you show dotted lines like this, I think it's called ferrite or firite core. I might not be pronouncing it right. But what we're interested in is these 2 solid lines like this. And that means you have an iron core. And so all power transformers, those are the ones that you plug into the wall to use for to charge your cell phone, or if you go out to the utility pole, or when Jacob mentioned, step up and step down when you're transmitting power. Those are all power transformers, and that's what we're going to talk about in this class. The air core, we will talk about that in communication electronics. And the other one, honestly, I don't really know that much about that one. I don't have much experience with the other one. So I've only dealt with air core, and when I took my communications courses, probably 99% of the time we're talking about power transformers. So that's what we're going to talk about. The side of the transformer where you hook the power, it's called the primary coil, or primary for short. And the side where you hook the load, secondary coil. You just drop the word coil, we call it the secondary. So we talked about that. Now, with most transformers, it doesn't matter which side you make the primary, which side you make the secondary. Say I have right here, if I have the turns ratio is greater than 1, then you know that that's a step-up transformer. So whatever the voltage here is going to be multiplied by the turns ratio, and you get a bigger voltage over here. But if you take the voltage source and you move it to this side, and take the load resistor and move it to that side, then this side now will be the primary coil, and there will be a step-down transformer. So a basic transformer, you can use either side as the primary or the secondary. Now that's not true of all transformers. Just a basic transformer, you can do that. There's nothing wrong with doing that. And so we talked about that. And then finally, the last thing we talked about are phase dots. So sometimes you'll have either 2 dots on the bottom or 2 dots on the top like that. And that just means your primary voltage and secondary voltage or current are in phase. If you see a dot here and one down here, that means your primary voltage and your secondary voltage or current is out of phase by 180 degrees. Most of the time that doesn't matter, but depending on what you're doing, it could matter. So you should be familiar with the phase dots. And then after we went through some of the theory and all the discussion around it, we came up with some equations that I wanted you to remember. We derived some equations, and those are the ones we're going to use to solve problems. So we derived, the most famous one is called the transformer equation, and that says that V sec is the turns ratio times V prime. So we got that one. We got the fact that I sec is 1 over the turns ratio times I prime. So these two are important. To get the turns ratio, we said that the turns ratio is defined as N sec over N prime. And we derived this one from an equation that you probably should remember. The equation is that, I put it over here, P primary equals P secondary. And because of that, the equation I will write, and I'll have you remember, is that P prime times I prime is equal to V sec times I sec. This equation right here will be useful when you're doing your homework. So the main two equations, though, are this one and this one. And of course, you got to use that one to get the turns ratio. And then you'll use this. You'll see where you use that. So that's kind of where we ended up. And then I promise you that I said when we come back, we got all the equations, you got all our tools, and now we can practice, we can solve a problem. So let's do a practice problem. So I do have documents, but I don't have them posted. So I'll just read it. So you have a transformer. This is a single-phase transformer. The turns ratio is 1 to 2, and the voltage source is 50 volts, and it has a 1K resistor hooked to it, and they tell you that the efficiency of the transformer is 100%. They want you to find V sec, I sec, P sec, P prime, and I prime. Now you're probably saying, well, that's confusing. So let me just draw the picture, and you'll see it. I'll just draw it as a circuit instead of reading it. So here's what we have. We have a transformer hooked to a 50 volt source. The load resistor is 1K. And the turns ratio is 1 to 2. And they want us to find V sec.
This is out there, by the way, just a heads up.
Oh, this is out there?
Yeah, you put it on there last time.
Okay, thank you. All right, well, guys, if you have it, then you can go ahead. I won't have to read it to you. So V sec I sec, P sec, P prime, I prime. So that's what we want to find. Now, I'm going to give you a second just to do this problem. Before I do that, though, let me point out one little thing that might be confusing. This notation right here. That notation. In math, you would write that as 1/2. But see, the 1, that 1 right there is in pi. The 1's on that side, and that 2 is in sec. So if you do it like that, then you'd have n pi over n sec, which is not what we want. So in math, even though this means 1/2, don't think about that. Don't think about it like that in engineering. What you want to do is just know that the number on the left, that's in pi, and the number on the right, that's in sec. And then use the definition for terms ratio that I gave you before to solve it. Don't do it this way. You got to reverse that. So hopefully I'm not confusing you. So I'm going to be quiet for a minute. You want to find these values, or if you have the paper off a blackboard, print it out. I'll give you, this is pretty quick and dirty. I'll give you a couple minutes to do it, and then I want to go through the calculations. So go ahead, see what you come up with, and then I want to show you something else. Oh, I don't know why I erased that. Okay, see what you can do with that. All right, let's go ahead and do this real quick. So the first thing we got to do is figure out our turns ratio. And as I said before, definition for turns ratio is N sec over N pri. Our N sec is at 2 right here, so we got 2 over 1. So we get 2. For our turns ratio, since it's greater than 1, we know that this is a step-up transformer. And then we can get V sec using the transformer equation right here. So if we use that equation, and by the way, when they give you the rating for a transformer, really actually any device, the voltage or current rating they give you is always RMS. So like, notice, is this peak? Is it peak to peak? What is it? Well, if it's anything other than RMS, I have to label it. But if you don't see any label, any notation, you assume it's RMS. So that 50 volts is RMS. So we know that this is 2. So since I know that's 2, I can use the transformer equation to get V sec. So V sec is going to be N times pri. We got 2 for the turns ratio, and my primary voltage is 50 volts, not 10 volts. So I got 50 volts, which means my secondary voltage is 100. So I have 100 volts from there to there. That means I have 100 volts across that resistor. So we got that. This is easy. If I know the secondary voltage, I get the secondary current. Notice the secondary current depends on the load resistance. So that's pretty easy for me to get. So secondary current is by Ohm's law. I mean, you could use this, but by Ohm's law, I sec is just V sec over my load resistance. So it's best to just use Ohm's law for that. So I got 100 volts, and I got a load resistance of 1K ohm. So I got 100 milliamps for my load current. So we got I sec. Now, for P sec and for P pri, remember that we're assuming transformers are 100% efficient. Now, if they weren't, the calculation would be a little bit more complicated. But for this class, we're going to assume an efficiency of 100%. We'll always do that. So because they're 100% efficient, then I can write this. And I can only write that because I'm assuming the transformer is 100% efficient. Well, we can get P sec easy. It's just V sec times I sec. And we got both of those values already. So we said this was 100 volts. And this is 100 milliamps. The current is 100 milliamps. So we got 10 watts. 10 watts. Now, okay, yeah, we'll just go with 10 watts. Now, that's kind of incorrect, but it's okay. We'll go with 10 watts. But the only reason I'm saying that is these are inductors, so the unit of the transformer will be volt amps. You know, we talked about AC power. Don't worry about it if it's applied to transformers, but just strictly speaking, these will be volt amps. But this resistor will dissipate 10 watts. So it doesn't matter that the transformer is rated in VA. That doesn't matter. because the 10 watts will appear at the resistive load. And now we have another load that's not resistive, then we got another problem, but we're going to keep it simple. So we found PSAT, and since we're assuming efficiency of 100%, we've also found P prime. Well, these will always be equal. Now to find I prime, you could use that equation that I used, but I always use this power equation. And I'll show you why I use this. I prefer to use this than the one I just erased. So we use this, we just solve this for I prime. If I divide both sides by V prime, then what I get is this. And I can solve for I prime that way. I prefer to do it that way. So we'll go ahead and do that. And then I got something else I want to show you. So I prime is going to be VSAC, which is 100 volts, times ISAC, which was 0.1 amps, divided by V prime, which is 50. So we got 0.2 amps, 200 milliamps. Makes sense because if we have, remember the trade-off is that if I step the voltage up, the current's going to drop. So if I step the voltage up from 50 to 100, my current's got to drop. If I go from this side back to this side where my voltage is dropped, my current's going to be higher. So it's twice as much current in the primary, but only half the voltage. And the combination of the P prime and the PSAC, they have to stay equal. So that's a very, very simple calculation. Okay, so any questions over that? Did you guys get the right answer, everybody? I mean, this isn't exactly rocket science. It's just kind of, using the equations that I give you. More so here, you want to understand the theory. And I think the theory, it's not very abstract. You can kind of see it. The most abstract part about it is just looking at Faraday's law, which this is what this is based on. But other than that, it's pretty straightforward stuff, I think. Now let me show you something new, something else you can do here. And this will help you with your homework. Right, multi-tap versus multi-coil transformers. I want to talk about those. So what is a multi-tap transformer? Okay, well, let's go back to our basic transformer. See, I told you that, let's just go what we had before. So if I told you the turns ratio is 2, right? I told you the turns ratio is 2. I'm going to hook up I don't know, make it 16 volts AC. So I got 16 volts on my primary. And then you already know over here, I'm going to have twice that. I'm going to have 32 volts. If I told you that N sec equals 1,000 turns, you got 1,000 turns on the secondary coil. And then I said, all right, I want you to count them. Find turn number 500. So you go in there and you count. And you figure out that the 500th turn is right there. That's turn number 500. You attach a wire to it and you bring it out like that. That's what I mean by a tap. If I go right in the middle of it, if I got 1,000 turns, right at the 500th turn, if I connect a wire there, then this is called a CT. That stands for center tap. And if you center tap the transformer, then this would be the CT, the center tap. And if you do that, what you have now is you have 3 circuits. You have this circuit right here, which gives you 32 volts AC. And then you have this one that's 16 volts, and this one that's 16 volts from there to there, or from there to there, if you center tap it. And so many transformers are center tap. Matter of fact, the one that we do when we get the lab, when we do this, our transformer lab, it's a center tap transformer. Well, if you look at this, this says multi-tap, not center tap. This says multi-tap. A center tap transformer is just one tap. So that might suggest multi means many. That might suggest to you, well, okay, I have to go to number 500. Can I tap it anywhere else? And the answer is, of course you can. Yeah, you can do that. Matter of fact, that transformer on the secondary side can have as many taps as you want. It can have many taps, and depending on where you tap it, you can use that turns ratio equation to figure out the voltage at that tap. Now, one application of this, I don't know if you guys ever popped open your, if you got not a laptop, but a desktop computer. Inside the desktop computer, there's a unit called a power supply. So it's usually in a big old metal box, at least it used to be. And if you pop that open, the biggest thing in there will be the transformer, the power transformer. So what happens is when you plug your computer into the wall, you got 120 volts. Well, most of the circuit boards in the computer are way less than 120. We probably got some 5-volt boards. I wouldn't be surprised to see some 12-volt boards. You won't have a 120-volt board. So what you got to do, you got to do 2 things. You got to take the 120 volts from the wall outlet and step it down to something more closer to the actual DC voltage that the computer needs, and make sure you realize that it is DC, even though you plug it into the wall. So what the power supply does is that transformer inside the power supply is a step-down transformer to take it from 120 to something close to whatever the motherboard and the memory, whatever that's what might need. Once you get it down close to a lower level, then there's other circuits in there called rectifiers that take the step-down AC and converts it to DC. And this is the kind of stuff we'll talk about if you take the electronics course. I think Ray Ellington teaches that. So I can have a multi-tap. So if you open up your computer and you open up the power supply, you'll see many taps in there, because you know they might tap it at 5 volts because you need a lot of digital circuits need 5 volts. They might tap it at, I don't know what the voltages are, but the point is you can have as many taps as necessary and get different voltages all off one coil. That's a multi-tap transformer. And I think one of your homework assignments, you deal with that. I think it is. I'm not sure. Well, how does that compare to a multi-coil transformer? What's that look like? Well, let me show you what that looks like. A multi-coil transformer. multi-coil transformer, what you have, you got a primary coil. But you can have 2 or more secondary coils. They're not center tapped, actual physical coils like this. So that's a multi-coil transformer. And now what you have over here, you got your primary terms. But over here, you got 2 secondary terms. You got that's a secondary term, and that's a secondary term. So we usually call one of these 1 and 2 and 3 and so forth. And to do the math here, to do an analysis, it's really simple. All you got to do when you're doing an analysis is, let's say I want to work with that coil. Let's say I got resistors hooked to both of these. When you hook a resistor to the secondary side of a transformer, we say the transformer is loaded. Loaded. A loaded transformer just means you got resistors hooked to the output. The output is the secondary coil. So let's say you got a resistor here, a low resistor 1, and here you got another low resistor 2. So these are loaded. If you wanted to do an analysis on this, it's the same as what we've already done. All you do is cover that one up and act like these 2 coils are the only one that exists. And you do your calculation for that. Once you're done with that, you cover this coil up and act like these 2 are the only ones that exist, and you do your calculations for that. And then you're done. Now, there is one small little thing here. Remember I told you that when you find current in the primary, you can use this. You can use this. If you know this and you know the turns ratio, you can solve for I pri. And I said I know that. I always use this. I use the power equation, V pri times I pri equals V sec times I sec. I use this equation to solve for I pri instead of this one. Now, this is the reason why right here. A lot of students think, let's say you find the current here in this coil, and you find the current here in this coil. Let's just make some numbers up. Let's say over here, I got 5 amps. Over here, I got 2 amps. Okay, so then you want to use that, and you want to solve for this. So I sec. So you might say, I got 7 amps on the second. Well, that wouldn't work. You can't just add these up and say you got 7 amps. This equation breaks down when you have multi-coil transformers. This one right here never breaks down because it deals with energy. So we don't really care. You know, you cannot add currents like this. But what if I told you you had 12 watts here and 3 watts here? You got this power and this power. You cannot add 5 amps and 2 amps and say the secondary voltage is 7. You can't do that. You can say, I got 12 watts here, I got 3 watts here, my total secondary wattage is 15, and since I know that P pri is the same as P sec, if I got 15 watts over here, I got 15 watts over here. And because you will always know V pri, you always know that, then it's easy to find the current over here. Is V pri times I pri. So if I know this and I know this, I can solve for I pri easily. That's why I said earlier, I never use this equation. You can use it if you know what you're doing, but sometimes it doesn't work. This always works. So when you go from a power energy point of view, it makes life a lot easier. You can do whatever you want to do. I'm just telling you what I like to do when I'm doing these kind of problems. So it's 3:30. I thought what we do is I want to practice. I want to show you because you got, I don't know, I probably gave you like 3 or 4 of these kind of problems. And so I figured we'll do one together. So let me give you a multi-coil homework problem. And take out a clean sheet of paper, or it doesn't have to be clean, but a blank sheet of paper. And I'm going to give you one of your homework problems that I'm going to post for you to do. And I want you guys to work it. All right, so let me see what I got for you. All right, so here's the problem. I want you to do this problem. All right. You have a multi-coil transformer. We're applying 120 volts at 60 hertz on the primary. And they tell you that you have 100 turns on primary coil. You got 1, 2, 3 secondary coils. So I just put these all as in, but you probably want to call like in sec 1, in sec 2, in sec 3. I just didn't have enough room to write that. But you have 3 secondary coils. The first one has 250 turns, the middle one has 200 turns, and the bottom one has 40 turns. These are all loaded, which means you have low resistors hooked on it. So again, you might want to call this low resistor 1, low resistor 2, low resistor 3. Low resistor 1 is 1.5K, low resistor 2, 1.2K, low resistor here is 120. You want to find V sec 1, 2, and 3. So find all the secondary coil voltages. You want to find I sec 1, 2, 3. So find the current in all of these coils. You want to find I primary. So find the current over here in the primary coil and find really, I guess that's it. You probably, probably want to find P secondary, all the second P sec 1, 2, and 3. I would find those because it'll make the rest of the calculations easier. So solve this for voltages on the secondary, currents in the secondary, current primary, and power on the secondary, and I guess power on the primary. We should probably do too. So see what you can do with that, and then this will be the last problem of the day. I think we'll be pretty much out of time after that one. So see what you can do with it, and we'll check it out. Okay, you guys ready? What'd you get for answers? Tell me how to solve it. What did we do? We kind of already walked through it a little bit.
The first thing that I did was find the turns ratio for each of the three combinations.
Okay, that sounds like a good plan. This, we'll call this turns ratio 1, turns ratio 2, turns ratio 3. Remember, the turns ratio in general is the number of turns on the secondary divided by the number of turns on the primary. And since the units are turns, we got turns here and turns there. The turns ratio doesn't have any units. So here I have 250 over 100. Here I have 200 over 100. And here I have 40 over 100. So here we get 2.5. So that's a step up coil, isn't it? And then here we get 2. So that's a step up coil. And then here we get 0.4. So that steps down. And then, oh, that's it. We only got 3 of them. So you notice that we got step up, step down. You can have that when you have these multi coil circuits. Okay, so now these are the turns, the secondary turns, and that's usually useless information. You want these little ends is what you want. So I'm gonna get rid of these. And replace it with this. So we got N1, 2.5. We got N2, 2, and N3, 0.4. All right, so what's next?
Multiplied each of the turns ratios by the primary voltage.
Okay, so he used it on each coil independently as if that coil is the only one there. So he used this. He took to find the secondary, he took the turns ratio, whichever one, I put an X there, times that primary voltage. So for here, we're going to take 2.5 times that. So tell me what you get if you take 2.5 times 120. What is that? It was 2.5. 300. So we got 300 volts across this resistor. And then if I take 2 times that, we have 240 volts across that resistor. And then if I take, that's 0.4 times that.
48.
48 volts across that. So this voltage got stepped up, this voltage got stepped up, this voltage got stepped up. Okay, so now we can find the secondary currents using Ohm's law. I wouldn't use any of those other equations. Ohm's law is the most direct way to do it. So since we know the voltage across the resistors and the value of each resistor, we can just use Ohm's law, keep it simple. So for the first one, for this one, the current we'll call I sec 1. It's going to be V sec 1, which is 300 volts, over the load, which is 1.5 K. What's 300 divided by 1.5?
200
200 milliamps. So I guess I can use green. We got 200 milliamps flowing here. And then we'll do the next one. I sec 2. It's going to be 240 volts divided by 1.2K. How much is that one? $240 divided by
100 million.
I got 200 milliamps for that as well.
Okay. That's interesting. So this is 200 milliamps. And then the last one,
I got 400 amps.
you got 400.
I'm sorry, 400 milliamps, I think. 40 divided by.
Okay.
Yeah.
Okay. Yeah, we got 48 divided by 120. So you got 400 milliamps.
That
Okay. 400 milliamps. So we got all our currents. So a common mistake for students to do is to say, all right, if I want to find the current over here, all I got to do is add up 400, 200, 200. My current over here is 800 milliamps. If you do that, you're wrong. You can't do that because the ratios don't work out that way. What you can do is find the power in each coil here, add those up, and that will be my total power over here, since I'm assuming 100% efficiency. So that's fine. All the power dissipated on the secondary sides. And then let's get our total power. So this is just V times I. So I got 300 times 0.2 is what? 300 times 0.2.
60
Is
watts.
that 60 watt? That's red. I can't use red again.
We're calling it watts, right? Because we're talking about across the resistor.
Yes. Good point. So this is 60 watts. Okay, for that one. And if I do again V times 0.2 for this, it'll be what?
48.
48?
Yes.
Okay. And then the last one will be what?
19.2.
All right. So P sec if you add these up, 60, 48, and 19.2, give me a total.
It's 127.2.
Right? 0.2, 127.2.
Exactly.
So, is that right?
Yes.
127.2?
Yes.
Okay. And that's going to equal P pri, because remember, we're assuming we have 100% efficiency. Now, the reason I want that is they're asking to get the current over here in the primary coil, and you just use Watt's law. P pri is V pri times I pri. So I is just going to be P over V. So if I do P over V, I get I pri equals, what was V? P is this, 127.2 watts. And V, did I not give you V?
No, it was 120.
Okay, so 120. So what's my answer here for current?
1.06 amp.
And then that's it. So that's it. That's not really, it's not hard. I mean, it's not hard. What I like about transformers, it's just kind of in your face. You can see it. So the math, the physics, all that makes sense if you understand Faraday's law and some other basic principles. They don't have any moving parts, so transformers usually last forever. They don't have any moving parts. So that's it. Now, there is one more, and I've already mentioned it. There is one more application of transformers, but it's going to take me quite a bit of time to go through that. So we won't be able to do it today because we'll go way past 420. But I mentioned impedance matching. Now, what is impedance matching? Well, let me just say a little bit about it. And then anybody have any questions over what we did? You guys remember in DC when we Thevenized? Remember Thevenin circuit? So Thevenin's theorem said that you can take basically any circuit, and you can represent it as a circuit that has two components. A resistor called the Thevenin resistance, and a voltage source called the Thevenin voltage. That's what we learned in DC. You also learned that whenever I hook up here, the original circuit, my load resistor, you learn that as long as my load resistance is equal to my Thevenin resistance, then we'll get maximum power from the voltage source to the load in the original circuit. So I'll review this again next time. Well, what happens if you have a mismatch? What happens if you have a situation where you have a mismatch? This is not true, but you still want maximum power. Now, this only works in AC. What you don't realize yet, the Step's theorem is not just a DC theorem, it's just the electrical theorem. I could have an AC source here. And we'll actually do some AC Thevenin in here. We'll do some of that. So we'll see. But if I have a situation where RL and RTH are not equal, but I still want maximum power transfer, then what you can do is remove the load, and in between the load and the device you have the load hooked to, you can put a transformer. You can take your load, put it over here on this transformer, and you can actually force this equation to be true and still get maximum power transferred from the power source to the load, from the amplifier to the speaker, from whatever to whatever it is that needs out. When you use a transformer for that purpose, it's called impedance matching. And so next time we come back, that's what I'm going to talk about. We'll talk about impedance matching. Well, now, we're supposed to go up to the campus, so I'll figure it out. I don't know how we're going to do it right now. We got to get through impedance matching, and we got to do filters. So we got impedance matching with this. We got filters. We're supposed to do superposition, this theorem, and then we got three-phase power. I don't know how many more days we got. I need to count and see. But I never really get to three-phase, to be honest. We'll see what we do. I'll be very surprised. But on top of that, we got to do some more. We got to do some hands-on stuff, else it wouldn't be fair. So I don't know if we're gonna meet Monday. I'll text you because today is only Wednesday, and hopefully the dean would have responded to me for. But even if we do go to the campus Monday, I can still show this at school. I can still go over this, and we can still do some hands-on stuff. Now, if we do that, we'll have to kick the class back to 1 o'clock because some people have, because of the way we arrange the schedule, a couple people in the class have other obligations. So I want to make it so that we can go up to the campus, we can do some hands-on stuff. and everybody can still meet their obligations. So we're going to be very, very flexible with what we do. So some kind of way I want to get this in. So go ahead. I'll put the homework up. I'll go upstairs now, put the homework up, work on that, and then I got some impedance matching stuff if you want to read about. This is the one area where your book does an okay job. The only thing about your book is all the loads are resistive. So when you have only resistors, it's not really properly called impedance. Impedance is when you have resistance and reactance. So he keeps it easy, and he just uses impedance. He just uses resistors. So we're resistor matching, but if you wanted to do impedance matching, you could. In the real world, it's impedance matching, and I'll mention that next time we get together. So I think that's all I have. Anybody have any questions for me, comments, whatever?
I have something unrelated to class.
Okay.
It's not personal though. It's still about electronics.
Okay, that's fine. Well, guys, if you want to sign off, you can. I will post the homework. I got it on my computer. I just got to put it up on Blackboard. I'll post that. When I get it posted, I'll send out the link, and you guys can start working on that. Okay, and you guys have a great rest of the day, and I'll see you later. Jacob, you want me to turn the recorder off or on, or does it matter?
It's totally unrelated to this. Actually, more like DC stuff. So.
Okay, I'll turn it off. Let's see here. Stop recording.